Hello, welcome back. So today we will be introducing a new concept called frequency analysis. So far we have seen transfer function of a system as a way to describe the whole dynamics of a system in a very compact way. And we have used that to showcase the power of that method. We used it in block diagrams to create more complex systems using smaller building blocks. We have seen the usefulness of transfer functions in analyzing the stability of the system. And here we open a new chapter that is probably, if not the most important application, one of the most important applications of using transfer function in a system analysis of dynamical system, and that is frequency analysis. To begin this topic, let me start by showing you these two punching bags. So the small one and the big one, I don't know the names, but I've seen it in the movies, that this one is kind of for training very fast movements and coordination of movement. The bottom one is mostly used for, I suppose, strength training, but I don't know, I'm not a boxer. But there is a very curious difference between the two, and that is the way you interact with the two systems. So imagine that the strength of your punch is somehow proportional to the weight and properties of this, and the only thing that you're changing is the frequency of the punches. For the small one, as you have seen in movies or you have experience with, you need to provide very fast punches for it to oscillate back and forth at a kind of desired way. But for the bigger one, you provide much slower sequence of punches. And if I want to plot again, assume that the strength of the punches are proportional to the size and weight of those, so don't worry about those. For the bigger one, well, let's start for the smaller one. So if you give slow pace punches, really the system isn't excited as much and you don't get a lot of useful oscillation out of it. But as you increase your frequency, you get to resonate with the system, and the amplitude of the movements increase, and possibly there is a sweet spot that you have to provide your punches. This is the frequency of your inputs or punches. So this is for the smaller bag. Conversely, for the big one, you need to provide kind of well-paced and slower punches, and at the lower frequencies, you start to provide enough input to the system such that it starts to oscillate back and forth. And if you increase your frequency of punches beyond certain point, you actually slow it down. So this is for the big one. And maybe another example of this phenomena is when you are pushing someone on a swing. So as you can, when you push someone, as the person is going forward, if you keep providing input as they are coming back, you are essentially slowing down and you're not doing anything constructive. But as the person goes forward and comes back, you give a push. Goes back and comes in. At this specific frequency, if you provide this push, you can create very large oscillation with relatively a small amount of input. So this whole thing, the way a system responds to different frequencies of input, is the idea of frequency analysis. And we'll see how we can formalize this or write it in mathematical form to generate generalizable argument about these behaviors. So these punching bags and kind of discrete punches are a little more complex to analyze, but something more useful that we can very easily define and work with is finding the response of a system to periodic input. So the goal is to characterize response to periodic inputs. And I should add here, let's put linear time invariant systems. Characterize input response of linear time invariant system to periodic input. And specifically, we are looking at inputs that look like a harmonic or sinusoidal input. So P is some amplitude of the input we provide to the system, and we are putting that at a frequency of omega. So essentially, my input is something like that. This is input, and it has some amplitude P and frequency omega that is related to this period of oscillations. So let's take a moment to discuss why this specific type of input. There are a few reasons we would like to analyze the response of a system to this type of input. One is, this is a very common input. So whenever we have rotation, we encounter that input. And a few examples of that is in a mechanical system, when we have a motor or anything that is rotating, this rotation, if there is, for instance, any imbalance in the system, creates these sinusoidal forces onto the system. Again, going back to rotation, generators that produce electricity also rotate, and because of that, they generate voltages that are sinusoidal, and the entire power network is some sinusoidal voltage. So not anything, but most of the things we study in power electronics or power electrical engineering is sinusoidal. Another way to think of it is, remember, if we have any kind of arbitrary input, we can break it through Fourier series, break it into individual components of sinusoidal at different frequencies. So essentially, any arbitrary waveform is a combination of a lot of sinusoids. And also, last bit, it's not a motivation, but a curious observation that, remember, whenever we have a linear system, the response, either the natural response, the step response that come out of the characteristics of the system itself, almost always contain some kind of oscillation, either an undamped oscillation or a damped oscillation. But nonetheless, we see these sinusoids in the response of linear systems. So in some sense, it makes sense to try to see what happens, for instance, if we supply the output of a system as the input to another system. This similarity is curious that we can start to think about. Okay, this is the goal. And maybe I can add one more bit to the goal. We want to characterize the response of a linear time invariant system to periodic inputs. That looks like that. We want to study only the steady state response. And by this, I mean whenever the effects of the transient response or the response of the system due to its own initial condition has died out, and what remains is essentially the only component of the response that remains is the forced response due to the input. So that's what we call by steady state. All right. Maybe I can start by formalizing the problem here. So imagine we have a transfer function, g of s, that is our x of s over u of s. I take u as the input because I run out of notation. This one equals k, some constant gain, and my transfer function has a bunch of zeros, s minus z1, s minus z2, dot dot dot, and a bunch of poles, s minus p1, s minus p2, dot dot dot. So this is my transfer function, and the input, I mentioned the input to the system is sinusoidal, so it is this input, so it's going to be p, and if I take Laplace transform of that, p omega, well, let me write it s squared plus omega squared. So if we have this, my input, excuse me, why do I have x? I don't know. Notations are confused. This could be y. Let me put y. Makes more sense. Yeah, let's do that. Let's call this, just to be nicer, let's call this x of s. I wrote again the same thing. Y of s over x of s. Maybe that's better. So input is x, and my y of s output. If I want to find y of s, I multiply the transfer function by the input. So my input is p omega over s squared plus omega squared times my transfer function k s minus z1 dot 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 s minus p1 dot dot dot. So this is my response to the system. So because we start always from zero initial condition, I hope you see it down here. I'm not too sure. I hope so. Because we always start our system in this transfer function terminology or notation from zero initial condition, it takes some time for the system to come to the speed with the input. So there is some transient phase before the response reaches the steady state. And the transient is usually defined by the terms here. If I want to find y of s, let me rewrite it, y of s equals pk omega 1 over s minus j omega. I'm going to break this down into two terms. Times s plus j omega. That is my s squared plus omega squared. Let me now close this. I keep writing, and here I have all my s minus z1, s minus z2, dot dot dot, z2, dot dot dot, s minus p1, s minus p2, dot dot dot. So that is my full response. If I want to solve for that, we learned we can do partial fractions. So I have a bunch of poles, minus j, plus j omega, minus j omega, and a bunch of p's. So in the end, I can write things like so, that I have s minus j omega, s plus j omega, s minus p1, s minus p2, dot dot dot. And I give these names a bar, and some b1, b2, and so on. And remember, there could be some complex conjugate pairs among these and some repeated poles, but that's fine. We write it as this general form. One thing to note, that all of these terms, and something maybe I forgot to mention, here, let me put the star. We are exclusively looking at a stable system. Because if the system is unstable, meaning that any of these poles, p's, have positive real part, this response will be eventually dominated by that unstable pole, and the response will blow up to infinity as time goes to infinity, and we will never have this kind of a steady state response. So because of that, this entire analysis is conditioned that the system is stable, meaning that all real part of all pi's are negative. So if we have this condition, so any of these terms other than the two ones that are related to the force response, all other terms will eventually will give me response that looks like some maybe t to the power of something, k e to the p, some pit. Maybe there are some sines and cosines, sine of something t. So all of these terms that come from individual poles, they all eventually go to 0. This shouldn't be pi, this is not exact, but it's fine. The point is, all of these terms, the corresponding equations in the time domain will include some exponentially decaying functions that could go to 0, and the only terms that remain as time goes to infinity are those that are determined by these two terms. So my y of steady state, it only includes these two components, a over s minus j omega plus a bar s plus j omega. So this is going to be my steady state response. And I'm not going to get into detail of exactly how to calculate these two. It's not complicated. It's a few lines. I want you to follow it. The calculation and derivation is in the textbook. However, I skip a few steps and show you the final value that this y of a steady state of s will eventually be p the amplitude of the input, over 2j. What I have here is g of j omega. I'll explain what that is. G of j omega over s minus j omega minus g of minus j omega divided by s plus j omega. So this p is the amplitude of input, a constant parameter. G of j omega is this g of s, whatever this term is, evaluated at s equals j omega. It is also sometimes called g of s. G of j omega is called the sinusoidal transfer function. So it is the same transfer function, same form, only evaluated at j omega instead of any individual s. And similarly, g of minus j omega is the value of g when s equals minus j omega. So this is the response of my system, characterized by the transfer function g of s, given the input p times sine omega t. So I ran out of space. I will clean the board and I will start again from this step to continue the derivation. So I rewrote this here again. And just to recap where we are, y of s, the output of the system, we know it's g of s, the transfer function multiplied by the input. The input is a sinusoidal with such a Laplace transform. The steady state value or the steady state response at the end of the day contains two terms that are determined by the input and somehow modulated by the transfer function g of s. And this is what we arrive at. And g of j omega is g of s, the transfer function evaluated at s equals j omega. So this is just a complex number, j omega. And if you plug it into the g of s is a complex function of variable s. And at the end of the day, when you evaluate it at j omega, you get some complex number. Remember that g of j omega is just a constant complex number that is dependent on omega. So now I have this, I have s, and this complex number, some z, and this one is the complex conjugate of the same number. So remember, if I want to write this, so g of j omega divided by s minus j omega. If I take the inverse Laplace of that, remember this is just a number, z, times 1 over s minus j omega. So s minus another number, s minus a. So this one, s minus a e to the minus, well, this case is going to be s minus, yes, it's going to be plus, yes, this is j omega t. And this one is just a constant, so it doesn't apply. So it comes out, and I can rewrite it as g of j omega e to the j omega t. So using this and trying to find the inverse Laplace of my steady state response, p over 2j is constant, so I'm going to take it back to time domain. Y of a steady state is, this is constant, t over 2j. This one, remember, g of j omega is constant, that, it becomes this. So I have g of j omega e to the j omega t, that's the first term, minus g of minus j omega, again another constant number, e to the minus j omega t. And again, if I continue write it here, so g of j omega, it's some constant number j. I could also write it in polar form. It's g of j omega, the norm, e to the I or j, the what do I have here? J phi, right. J phi, where this phi is, let me write it this way. No, this was good. Let's keep it as phi, and this phi is angle of g of j omega. So I'm just representing the same number in polar form, and I want to do that here. So I have p over 2j, norm of g of j omega, e to the, I'm going to keep it as phi for brevity, e to the j phi, e to the j omega t, minus, same number, g of minus j omega, e to the j phi. But one thing to note here, that these two, g of j omega and g of minus j omega, are complex conjugate pairs, or complex conjugate of each other. So their norms are going to be equal, but their angle are going to be opposite of each other, and e to the minus j omega t. So these two are now equal. I can factor it out and combine these exponents. P over 2j, let me pull that out too. Norm of g of j omega times e to the j omega t plus phi minus e to the minus j omega t plus phi. It's getting shape. I'm going to take these 2j down here. Now this is a very familiar form, e to j theta minus e to the minus j theta over 2j. That is sine of theta. So I have p g of j omega sine of this, sine of omega t plus phi. And that is my steady state response. And here phi is angle of g of j omega. Okay. We arrived at what we wanted to do. But what does this mean? Let's recap. So I have a system defined by the transfer function g of s. I give it a sinusoidal input, and x of t was p sine of omega t. I give it this input. The steady state response is again a sinusoid with the same frequency as the input. So the response oscillates with the same frequency, but there is a phase shift, and also there is a change in amplitude. So to summarize, output, I should say a steady state output, is another sinusoidal, sinusoidal with same frequency as input, omega, but with phase shift with the size of g of j omega, and gain is the change in amplitude or the multiplication factor, and the gain of size of this g of j omega. So this is quite powerful. What it means is that the dynamical system that I have, if I know the transfer function, and if I calculate the sinusoidal transfer function, that is evaluating it at s equals j omega, then I can very easily construct the steady state output to a sinusoidal input with frequency omega, and I know, depending on what omega is, how much my sinusoid is shifted and how much it is scaled. So this is the essence of frequency analysis, or maybe not as a sense, but a very compact way to analyze the response of a system to different frequencies of input and see what happens to it. Is there anything I'm missing here? So no. So take this, and maybe I have to erase it because there isn't much space. Is there? Maybe I can fit it here. To look at one example, and let's go back to the punching bag that I had at the beginning. But a punching bag in general is a nonlinear system. Any pendulum is a nonlinear system. So let me first simplify the punching bag with this pendulum that is defined by angle theta. And let's assume I have some damping in my at the pin joint of the pendulum. So if I have this, if I write the equations of motion in nonlinear form, I have L is the length, L theta double dot plus B theta dot plus G theta equals the input. Let's call it, what did I have? Let's call it input F, whatever. Let me first write the nonlinear form. So this G is G sine of theta equals F. And now, because I cannot easily work with nonlinear system, let's linearize it. The linearized version is L theta double dot plus B theta dot plus G theta equals F. And F is some, you can think of it as a torque that is acting on this pendulum. And then F is the input, so the transfer function G of S, which equals the theta of S over F of S, is 1 over Ls squared plus Bs plus G. So that is my transfer function. Now if I want to know if my F, the input, is a sinusoidal, how does my response, the angle changes? To do that, first step is to find G of j omega, the sinusoidal frequency, which is 1 over L j omega squared plus B j omega plus G. And I can, J squared is minus 1, so I have 1 over B. Well, let me write it this way. First, the real parts to make it look nicer. So I'll have G minus L omega squared plus B omega j. So that is my sinusoidal transfer function, which is a function of omega. But nonetheless, it is just a complex number. So if omega takes a value 2, I have 1 over a real part plus some constant j. So it is just an imaginary number. And I can calculate my G of j omega, the norm, which is the norm of top divided by the norm of bottom. So it is going to be G plus L omega squared plus B omega squared. And, oops, my phase, this phase of G of j omega is going to be phase of the top with just a real number 1, so it has angle 0, minus tan inverse of imaginary divided by real, so B omega over G minus L omega squared. So these are the gain and phase shift of the response if my input F is some sine of omega t. The output theta at the steady state will have its amplitude multiplied by this number, and the response is going to be shifted by this amount. So to see it more in action, I have simulated this. So what I have here is I'm plotting the input, the sinusoid, and the response of the same system given a specific frequency. At this point omega equals 2, and I have calculated G of j omega equals 0.1. So input has amplitude 1 for simplicity. And you can see at the beginning there is some transient. It is not exactly sinusoidal, but toward the end it becomes completely periodic and sinusoidal. And the amplitude of this response is 1 amplitude of input multiplied by this number, and it is exactly same value, 0.11. And it is hard to see here. There is fairly a small change there is a small phase lag minus, well, there is some minus 3.8. Is that radians? No, that is degrees. So there is a very small phase shift, only 3 degrees, not very noticeable. And on the bottom, what I'm plotting is again these values G of j omega and the phase of G of j omega, just to have a visualization. As I increase my frequency, going to higher frequency, you can see my amplitude of response is going to increase. It is also shown here that the response is increasing. You can also see the amplitude of the response is increasing compared to here. It is increasing. It increases until it reaches some maximum value. And after that, again, the gain starts to decrease, and the phase lag becomes more noticeable. So now you can see the peaks are lagging much behind the peak of the input, and I am roughly at 135 degrees lagging behind. And eventually, as I increase, my amplitude will get smaller and smaller, and my phase lag is going to be eventually it will reach 180 degrees in its limit form when omega gets to infinity. So there's going to be a complete anti-phase relationship between the input and output. Maybe I can zoom in and see that the peak almost corresponds to the valley and vice versa of the input and output. So this is for the smaller punching bag, when the only thing I'm changing is the length of the pendulum to approximate the small and big punching bag. Let's see what happens if I look at the bigger one. No. Why doesn't it run? Let me see. Why doesn't it run? Well, I have to do this. It is running the top part for now. See how it looks like. And soon it's going to jump to this one. So this is the larger punch back. And as we were discussing later, you need much slower frequencies of input to be able to move this larger punching back and forth. And it is evident from the frequency response of the system that now the largest amplitude of the response happens at much lower frequencies. And remember, I've just only increased the length of the pendulum representing my punching bag. And in this case, at what we call the resonant frequency, the amplitude for this specific set of parameters that I have chosen, the amplitude of the response actually slightly gets larger than the amplitude of the input. It's 5% more. But this is all dependent on the set of parameters that we choose. It could be more or less. And similar to the other case, the amplitude reaches 0 as omega increases, and I converge to minus 180 degrees phase shift. So just by looking at the gain and phase of the two transfer functions for the bigger and smaller punching bags, I can readily see how the two systems behave differently under the same input given different varying frequencies. All right. So that's all I have for now, I believe. So that is the beginning of frequency analysis. We have just laid out the basics. And there is a lot more we can do with just this simple concept of this one, of just looking at the gain and phase shift that are fully described by this sinusoidal transfer function. In the next lecture, we will see how we can take these and make a very useful and practical tool for both analysis and system identification, and also a lot of other applications such as control design in a concept called body plots. So until then,